Welcome students. So we are discussing about the process of poll assignment or state feedback control. Already we have understood with the example that with this example we have understood that how the gain of the controller, state feedback controller, that is K, can be calculated. Okay, so this was the last slide where we have discussed that process of pole assignment for n less than equal to 2. If the order of the system is less than equal to 2, then it is suitable to find out the controller gain by direct comparison. What are the steps? Now for the step 1, select n desired eigenvalues lambda 1, lambda 2, lambda n, and if they are complex, their complex conjugates are also included. So after knowing the desired eigenvalues, means if we want to place the poles of a given system, then we have to know where the poles must be placed. Okay, now we'll in the step 2 we'll calculate the closed loop characteristics equation with the desired eigenvalues. Means with this lambda 1 and lambda n, we will find what will be the desired eigenvalues, that is s to the power n alpha 1 s to the power n minus 1 plus alpha n. Okay, now definitely this alpha 1 alpha n will be the real numbers. Now we will find out the characteristics equation of the closed loop system with this formula, that is determinant of si minus a minus bk. So this ak is, this also will be the characteristics polynomial, but it will be in terms of k1 k2 kn. Once we will get this, we will compare this desired characteristics equation with the characteristics polynomial of the closed loop system. Then we will get the values of k1 k2 kn. Okay, but here I'm telling the kn, but it is suitable for n less than equal to 2, so it is better to say k1 and k2. Okay, you can go for the higher order system also, but the process will be complicated, because as I told you that this advanced control theory, one important advantage of this advanced control theory is that all the algorithms can be solved using computer. So that's why we have to give the emphasis that how this controller gain can be calculated efficiently with the other algorithms for the higher order system. So that's why at the last class I told that other two processes also we are going to discuss, that to find out this k1 k2 kn, that state feedback gain, okay, using transformation technique and using Ackersman formula. Okay, so first I'm going to discuss using transformation technique, the process of pole assignment using transformation technique. So now we will see the assigning eigenvalues of a minus bk is particularly straightforward if the AB pair system is in controller canonical form. Now only you will understand that why we are going to give an emphasis before that to find out the controller canonical form, which is one of the standard form or standard form. Okay, so you know that is suppose that a system is given to you for which we want to do the pole placement. The A matrix and B matrix are in controller canonical form. So now we want to realize what the advantages we will get. Now once a matrix is given to us, we can directly calculate what will be the characteristics equation. You see the characteristics equation is to the power n plus a1 is to the power n minus 1, a2 is to the power n minus 2 plus an. The last row of the A matrix in CCF consists of the coefficient of the characteristics polynomial in reverse order with negative signs. Okay, so that is the way we can find out easily the characteristics equation of the open loop system. Now if we want to find out A minus BK, let us see what the form we will get. So now A matrix is this, then BK will be 0, B matrix is 0 0 1 and K1 K2 Kn. So you will find that only the last row will exist, and if you do the A minus BK and you will get this kind of matrix, and you see it is still in CCF. So if we want to find out the characteristics of equation of A minus BK, directly that can be written, and that is s to the power n a1 kn s to the power n minus 1, and last component of the characteristics equation will be an k1. So now if this is known to us, then you see, if we want to place the poles of the closed loop system at the desired location like lambda 1, lambda 2, lambda n, then we can find out the desired characteristics polynomial. There is alpha d will be like this. Then what we will do, we will just compare these two 10 and 11 to find out the k1, k2, kn, and you see the alpha 1 will be a1 plus kn, alpha 2 and alpha n subsequently, and from there we can easily calculate what will be the k1, kn minus 1 and kn. So now up to this it is very much clear that computational advantages we are getting if the system is already in controller canonical form. Okay, so now already we have understood, even if the system is if it is not in controller canonical form, we can find a suitable T matrix by which we can transform any given system to the controller canonical form if the system is controllable. Okay, if and only if the system is controllable, then any system can be transformed to a controller canonical form with the suitable transformation matrix T. Okay, so now what we will do, now we will use the similarity transformation to find out this controller gate k1, k2, kn. So that's why the key observation is that when the system is in controller canonical form, each control gain affects only one of the coefficient of the characteristics polynomial. You see that k1 plus kn only it is added with a1. Okay, k1 an. So now and this coefficient can be assigned arbitrarily by suitable choice of k1, k2, kn. Hence the name controller canonical form, convenient for controller design. And how we can use the advantage of CCF, now as I told you that now we will in general we will discuss. Means suppose a realization is given x dot equal to ax plus bu, y equal to cx. It is not in a controller canonical form, any form it is given. Okay, now it has been asked that find or design a suitable state feedback gain matrix K, okay, for a given pole location, suppose lambda 1, lambda 2, lambda n. Now what we have to do, now we know that if we want to design the state feedback matrix gain matrix K, so now the closed loop system will be x dot equal to a minus bk into x. Okay, now if we will use a similarity transformation to transform this system in controller canonical form, then the old coordinate x and the new coordinate x bar will be related equal to x equal to t into x bar. Okay, so now x bar dot is equal to t inverse x bar, and t inverse x bar in closed loop system, that is a minus bk into x. So a minus bk into x we have substituted in the place of x dot, and now it is very much clear that we are getting the closed loop representation in the transform domain. Okay, this will be the a bar, that is t inverse at. T inverse B will be the B bar, and now very interestingly we are getting K into T, that is actually the K bar. Then as usual it will be X bar. So this is the system in original domain, and this is the system in transform domain. And to do this calculation, our aim is to know that how the K bar means transform domain gain matrix and the original system gain matrix are related. So the relation is very clear, that is K bar equal to K into T. Means what we will do, we will calculate the gain matrix K bar in transform domain, that is in controller canonical form, and then what we will do to find out the K, we will multiply with the T inverse to get the K, means this relation. You see K equal to K bar into T inverse. When we give the example, at that time it will be clear. So what is the summary of the procedure? Now convert the CCA, controller canonical form, using suitable invertible coordinate transformation matrix T. And already in previous classes already we have discussed to transform any system in controller canonical form, how to build the T matrix. Okay, solve the pole placement problem in the new coordinates to get the advantages of CCF. Once you will transform the system in controller canonical form, you will get the advantage of calculation what I already have shown, and then at the last what you have to do, you have to transform it back to its original coordinate, that is to calculate the gain matrix K in the original coordinate. You have to multiply K bar into T inverse. Okay, so let us discuss this procedure with examples. Suppose we have a system x dot equal to ax plus bu, where A is not in controller canonical form and B, obviously the system is not in controller canonical form. Now the problem is given: design a feedback control law u equal to minus kx such that the closed loop poles all are at -1. So we want to transform that system, we want to place the pole of this system, all will be at -1, means it is a third order system, so all the three poles will be located at the -1. Use transformation technique. So we have to use transformation technique to design this K matrix. Okay, so just you follow the step, then easily you can design. Step 1, that we have to test whether the system is controllable or not. So we have to build the C matrix. So C matrix is B A B A square B. So if you find that determinant is not equal to 0, so then the rank of this controllable matrix is full, so the system is controllable. Okay, so now step 2 is to find the transformation matrix T. Okay, and we know that transformation matrix T is C into M. So we already found out C. Let us construct the M matrix. So how you will compute the M matrix? Now we have to find the open loop characteristics equation. So open loop characteristics equation, we will get S cube plus S square minus S minus 2. So S cube plus A1 S square plus A2S plus A3. Okay, so you can verify this system actually, the open loop system actually is a unstable system. Okay, so step 2 will be to build the M matrix. So M matrix for this 3x3 system will be A2 A1 1 A1 1 0 1 0 0. So accordingly we will fill the A2 A1 from the characteristics equation. Okay, now we have to compute the transformation matrix, which is the multiplication of the controllability matrix and this M matrix. So accordingly we build the T matrix. Now we can compute the T inverse. So T inverse is also calculated, and step 5 is to compute the A bar. So A bar will be the controller canonical form. You see 0 1 0 0 0 1, and the last row will be the coefficient of the characteristics equation in the reverse order with the negative sign, that is A3 A2 A1. Okay, so now we got 2 1 and -1, and B bar obviously it will be 0 0 1. Now we will compute the A bar minus B bar K bar. Now for the third order system, the K will be K1 bar, K2 bar and K3 bar. So A bar minus B bar K bar is easy to find. So you see it is in a controller canonical form. So if I want to find out the characteristics equation of this closed loop system of A bar minus B bar K, that is also very easy to calculate. So that will be directly written, that is in the reverse order with the negative sign. So S cube plus 1 plus K bar K3 bar S square plus plus of -1 plus K2 bar S plus -2 plus K1 bar. Okay, so now we can compute the desired characteristics equation, because already in the problem it is given all the poles of the closed loop system must be located at -1. So the desired characteristics equation can be calculated S plus 1 whole cube, that is S cube plus 3S square plus 3S plus 1 So now we will compare this alpha s and AKS. If you compare, then you will get K1 bar, K2 bar and K3 bar. But you don't forget to perform the last step, because this step is telling that you have calculated the gains of the controller in the for the transform system, not for the original system. This is with the this K1 bar, K2 bar, K3 bar in the transform system, for the transform system. So for the original system, last step you have to follow that K is equal to K bar into T inverse. So if you calculate, it is coming 1 1 1. So this is the control law which will place the pole of the given system at -1. Okay, all the three poles will be located at -1. So this is the way by which you can calculate the gain of the controller with this transformation technique. Okay, so now the next technique we are going to discuss, that is very easy to understand. This is a one-line formula. So Ackermann formula gives us a method of doing this entire design process in one step. The formula is one step, that is K equal to 0 0 1 C inverse alpha D into A, where this C is the controllability matrix and alpha dA is the characteristics equation for the closed loop poles, which we then evaluate for A is equal to A. Means we know that what is the desired characteristics equation. Okay, so the desired characteristics equation is what? Now already we have discussed at the beginning, that is desired characteristics equation is this: alpha dA is s to the power n, alpha 1 s to the power n minus 1, alpha 2 s to the power n minus 2 plus alpha n. How we will build this desired characteristics equation? Because we know that where the closed loop poles must be placed, that is lambda 1, lambda 2, lambda n. And from the Cayley-Hamilton theorem we know that if it is the desired, it is the characteristics equation of A. Okay, so it will satisfy this its own characteristics equation. So from there actually what we can say that we have to calculate this alpha D of A. Okay, so alpha D of A, that will be a to the power n alpha 1 a to the power n minus 1, alpha 2 a to the power n minus 2, then alpha ni. Okay, now from this formula it is very much clear that to calculate the gain K, then the controllability matrix must be invertible, means the system must be controllable. Okay, so these steps we will try to understand with the formula, with an example is x dot equal to the satellite example what we have taken. You see this example I have taken for a 2 by 2 system, but you remember that these processes are valid, means these processes you will get the advantage computationally when you will do with the computer when the order of the system is greater than equal to 2. Okay, so we know that for this system the desired characteristics polynomial is s square plus 8s plus 32. How we got this characteristics equation? That already we have discussed in the satellite example. Okay, now for this system we have we have calculated the controllability matrix, and similarly we can calculate the C inverse. Now if this is the s square plus 8s plus 32, then we have to calculate alpha D of A. So it is a square 8a plus 32i, which is coming 32 8 0 32. Now K will be 0 1 because it is 2 by 2 system, so dimension of the first matrix, the row matrix, will be the 1 cross 2. So 0 1 C inverse alpha D of A. If you substitute C inverse and alpha D of A, and if you perform this multiplication, you will find that 32 and 8 will be the controller gain, which we have calculated earlier also. So this is the way by which you can calculate the controller gain. So basically the three methods we have discussed, that is the direct comparison. Then we have discussed the transformation techniques, how by transforming the system in controller canonical form we can calculate the controller gain, and then at last we have calculated the Ackermann formula. So in your exam, if any method is specified, you have to solve the problem with that particular method only. If nothing is specified, then any method you can utilize to find out the controller gain. Okay, so now the last topic we will discuss, that is tracking of reference inputs. Means till now we have looked at how to pick K to get the dynamics to have some nice properties. Means definitely the stabilization problem. Means in all cases we have seen that maybe the system is unstable, then we want to place the poles at the left hand side of the S plane such that we can stabilize the A matrix. Means stabilize the closed loop system. Now the question remains as to how well this controller allows us to track the reference command. Means if I want to design a controller which will not only it is going to stabilize the system with the controller, but it is going to give a performance such that the system is able to track a given reference command. Okay, so to understand that one, let us start with the system that is x dot equal to ax plus bu, y equal to cx, and now we want to understand what is the meaning of that track a reference command. Okay, and this is the r is the reference input actually we want to track. Okay, so u equal to r minus kx. So for good tracking performance we want yt must be equal to rt, that is the tracking performance. Means the output of the system should be following the reference input rt as the t tends to infinity. Okay, so now we want to write this thing in frequency domain. So using final value theorem, limit t tends to infinity y of t is equal to here it will be s. So limit s tends to 0, s of ys. Okay, s of ys. So now for good performance, s of ys must be equal to s of rs as s tends to 0, which means that ys by rs at s equal to 0 must be equal to 1. So this is the mathematical requirement of a good tracking performance. Okay, when we will say that we are going to design a good tracking performance, we have to show that ys by rs at s equal to 0 must be equal to 1. So for good performance, tracking performance, the transfer function from rs to ys should be approximately 1 at dc. What is the meaning at dc? There will be no frequency. No frequency means s will be equal to 0. So let us look this example and this requirement with an example. Okay, suppose x dot equal to this axt plus b of ut, this kind of system is given, and if you will find the transfer means the characteristics equation of the system, that is a square minus 3s plus 1 equal to 0. So this system is unstable. Okay, now suppose we want to place the poles at a desired location, that is actually minus 5 and minus 6. So then the system will be definitely stable. Okay, but with the state feedback controller, that is minus k1 k2 xt. So now we want to determine what is k1 and k2. So now we can find out what will be the closed loop system, that is a minus bk, and the k is k1 k2, and we have the A and B matrix, so we can calculate what is the closed loop system in terms of K1 and K2. Now we can find out the characteristics equation in terms of K1 K2 of this closed loop system, that is s square plus K1 minus 3s plus 1 minus 2k1 plus k2 equal to 0. Thus by choosing k1 and k2 we can put the eigenvalues of ACL anywhere in the complex plane, assuming complex conjugate pairs of poles. Okay, so now if we want to place the pole at minus 5 and minus 6, then desired characteristics equation will be s square plus 11s plus 30 equal to 0. Now we will compare this equation with this equation to find out the k1 and k2. So we are finding that k1 is 14 and k2 is equal to 57. So now it is very much clear that with this gain, the poles of the system will be shifted to minus 5 and minus 6. Now the question is that is this system is able to track a step input? So to understand that one, we will see the investigate the closed loop system. So closed loop system will be after applying this kind of control, that is r minus our control law is r minus kx. If you substitute this one in x dot equal to ax plus bu, your closed loop system will be x dot equal to a minus bkx plus br, and the output will be same, y equal to cx. Okay, so now if I want to determine the transfer function of the closed loop system, that will be c into si minus a minus bk whole inverse into b, because that is the formula to find out the transfer function. Now if you compute the transfer function for this given system, it is coming s minus 2 by s square plus 11s plus 30. You see, this is the characteristics equation we should get, because we know that for the system poles must be located at -5 and -6. Okay, but if we assume that we are going to track a step input, then from the final value theorem we are observing that ys by rs at a is equal to 0 is minus 2 by 30, which is not equal to 1. Means it is not going to track the step input. Means some steady state error definitely will be there. So when, can you tell me when it is going to be, this ratio will be equal to 1? Now if we will multiply with minus 15, then it is going to be equal to 1. Okay, so now how can I provide this minus 15 here such that the ratio will be equal to 1? To understand that one, we will modify our control input. Okay, so now what we will do, previously the control input was r minus k into xt. Now we are going to give weight to the r, some weight we are providing, that is n bar. Now we have to see how this n bar is going to help us. Okay, what is n bar? Now n bar extra gain used to scale the closed loop transfer function. How? Now if you now apply this closed loop this control to the closed loop system, then x dot will be equal to a minus bk into x plus b into n bar into r. So previously you see only you got br, now you see you got b into n bar r. So now definitely ys by rs, if you calculate, then you will find that you are getting that closed loop system with that n bar is multiplied. Okay, now if you make n bar equal to minus 15, then definitely this ratio will be equal to 1. It means that the step input, for the step input, the output is going to 1, settle at 1 at t tends to infinity. Now the question is that in general how we will calculate this n bar. From this equation it is very much clear, because for the ideal case this ys by rs will be equal to 1, and c into si minus a minus bk inverse b into n bar will be equal to 1 when s tends to 0. So now if it is like this, then what will happen? You will get n bar equal to c into a minus bk inverse into b inverse into minus, that is minus. Okay, because negative sign will come from where? Here, because we have to calculate this at s equal to 0 and this ratio is equal to 1. So definitely you can calculate from that relation what will be the n bar. Okay, so now note that this development assume that r was constant, but it could be also be used if r is slowly time varying command. Okay, so here actually this procedure will be useful if you are going to track a very slow varying reference input like step. Okay, so now this same system is simulated using MATLAB. So this blue graph you can see, it is only with the control, that is u equal to r minus kx, means when we are not going to weight the r by n bar. So now you see we want the output must settle at 1, but we are going to settle at somewhere at the negative side, that is basically what we have found out, that is minus 2 by 30. Okay, so we are going to settle at negative direction. So now if we want to track it, then what we have to do, we have to multiply the r with the n bar, and we are finding that if you multiply n bar is equal to minus 15, then you see it is going to settle at minus at 1, means output is going to track the step input. So corresponding MATLAB code is there, and this is the all about the state feedback control. So here at conclusion, I want to tell that the state feedback control and pole placement techniques are very useful for the controller design, because here the design of the controller gains are very simple. So now basic thing is you have to remember that in your exam that some performance indices will be given. If the performance indices are given, from that performance indices your work will be to find out the closed loop pole location. Okay, sometimes you will find that in your exam directly the closed loop pole locations will be given where you have to place the poles. If it is not given, then some performance indices will be given. From there you have to calculate where the closed loop poles will be located. Once you know the closed loop pole location, then you can find out the desired characteristics equation. Okay, so now you have to follow that which any method is specified or not. If any specified method is given, from that specified method you can find out the closed loop gain matrix K to place the poles at the desired location. So now we are going to end the state feedback design, and only the last chapter is remaining, that is the observer design. Okay, now here you remember that when we are doing the state feedback design, then we have assumed that all the states of the systems are measurable. What are the state? What may be the states of a system? Mean for an electrical system, as I told you, that it may be the voltage current. For a mechanical system, it may be the position, velocity. Okay, so now it may happen that when we are going to deal with the real systems, some of the states will be not available for measurement. Okay, so now in the next class we will see how the observer can help to estimate those states, such that we can implement the state feedback control law with that estimated states. Okay, thank you.